Okay. And you are wondering what has that to do with Alaska. And it's about the climate regions and what our mean body exchange is with the heat. The reasoning for that talk is that in 2012 there was this big article in the Anchorage Daily News as they were really upset about Travel and Leisure, who published that Anchorage is the worst dressed city in America. And most people explained that it's the cold climate of Alaska, which of course is wrong. And because there is not just one climate. And it's also wrong, not because it's obviously Fairbanks. And we will find out now why it's wrong to say that Alaskans or people in Anchorage are the worst dressed people in the nation. First of all, what is climate? Climate is the statistical mean of the weather over 30 years. So given that, it can't be the climate the reason for being badly dressed. Well, you don't dress for the -3 degrees Celsius, 300 millimeter precipitation that we have here in Anchorage, right? You don't, because then you would look different than you look today. So, and there is not just one climate of Alaska. If here is some European, Alaska is as big from the Ural to Portugal, or when we project that onto the lower 48s, we have basically coast to coast. So when they can have different climate regions, so Alaska obviously has two. And actually the National Weather Service distinguishes several climate regions, or climate divisions as they call it. The North Slope, the interior, and they're subdivided in northeastern and southeastern, the central. Then they look at the west coast and Bristol Bay, the Aleutian Islands, and various climate regions in the Panhandle. However, as I said, we don't dress for averages, but for the actual weather. And so it's not very helpful to go with the definition of the climatologists or the climate science, but it's much better to go with a climatology that's established by people who are doing research on ecosystems, because certain plant groups and animal groups just live between certain temperature ranges and humidity ranges. And that is what Köppen and Geiger did more than 100 years ago, divide the climate of the Earth into these regions that basically characterize the climate by general thing that's applying over the entire year, like a warm temperate climate. Fully humid would mean that it rains all year long, precipitation more or less equally distributed. Hot summer, you get the idea, right? And when you have snow in winter, that are the snow climates, and guess that's what we mostly are. Now, how does that look as an example when we take Anchorage, because that was kind of our first thing we started with? Then that's according to this climatology, CWC climate. That means warm temperate that's related to the ocean close by, that basically hinders that the winter gets very cold because the water has a heat capacity and keeps the air warm, and cool summers, and the precipitation is mostly in summer, that means in winter dry. Some climatologists or ecologists also put it at the DFC. However, I think that's not necessarily right, because Fairbanks is a classic DFC climate, and you see that that has also lower precipitation in winter, but it has a much wider temperature range because there is no ocean in the nearby. Now let's go to Juneau. and that has basically a similar climate like Cologne. And when we look for Barrow, you see that that's a real polar tundra climate. And yeah, the temperature here, monthly average temperature is in Fahrenheit. And here the precipitation in inch on this side. So the bars are the precipitation, the red curve is the temperature. So you see that we have already various climate zones with respect to living beings that would be able to live in these areas. So now how does it look when we do that all over climate? I pulled here the data for 25 years for basically 1900 to 2000 and chunked that into 50 years, 25 years. And you see that over these 25 years, the climate regions have, classifications have changed slightly. And that's because the weather is never ever the same one day or the other. So when you average over 25 years and have always kind of different changes in the weather, you can't expect that you would get exactly the same result for every 25 years. Take-home message out of this, it's natural that different time frames show different changes a little bit in climate. And when you look at this, you see that these are kind of at the boundaries to the climate region where you have these changes. So what we had here in Fairbanks over these 100 years is a shift from that we have dry summers or relatively dry summers to more moisture in the summer. So more rain, we saw that this summer really good. Sorry. You are all familiar with heat waves and know that they are dangerous, and you know that you look at the relative humidity and the temperature, and that the combination of very hot and very humid basically leads to the dark days. And they are called so because ancient belief is that the dark star is responsible for that heat. Of course it's not. You also are familiar with the wind chill, at least when you park your car in the parking lot. In winter, there is always windy and it feels really chilly. So wind plus low temperatures cause wind chill. Okay, so to protect ourselves, we are close. And what we want to do with them is basically we want to modify the exchange of our body heat with the environment. How do we exchange heat? We exchange latent heat, that's basically exchange of moisture, or in plain English, we sweat. Then we also have thermal heat exchange, that's by convection, conduction, and radiation. And because that's not so obvious, and we are not so aware of that, let me explain what that means. So you know that your the skin temperature is about 93.2 Fahrenheit. It's a little bit colder than your blood. And the air, on a day like today, it's about 75 degrees. And you see here this picture, and it has this greenish, orangish waves. What's happening there is basically the warmer air that's warmed by your hand, basically, because it's lighter, goes up. What also happens is, because you sweat and moist air is lighter than dry air, it's also going up. So you have some convection, like you have convection with the clouds. And when you have wind, that, of course, what happens with your body is that your heart pumps the blood through the veins, and they transport heat and to your skin. And when you have wind, it transports away the heat that's warmed by the air. And it's doing that faster the faster the wind is. And when you now start sweating, you get cooling by the evaporation of the sweat under your skin, and that basically cools you. So wind and your sweat, that makes you feel comfortable so that your body doesn't get overheated. So when you sweat now on a hot day that's really humid, what happens, and it's shown here also as a blue, when the skin gets really blue here, that's the sweat stays on the skin because the air is so humid that the sweat can't go into the air anymore. Then it stands there and it insulates your skin. That basically means that you start overheating even more because you can't get the cooling effect anymore. And when you are exposed to such conditions that are kind of 35 degrees, that's over 120 degrees Fahrenheit, and 100% humidity, and you stay in that condition 6 hours, you are a little bit dead. Okay. So, then the body also can conduct heat to the air. And conduction is a process where heat is transported just from one molecule to the other. You know that from your iron pan. If you put it on the stove, put in your eggs, and your eggs are good, you take a towel and not touch the iron handle, because you know that the heat conduction has heated the handle. So the same principle, the skin conducts heat to the air. So what happens when we are standing somewhere and are waiting for the bus, what actually happens is that we basically conduct heat through our soles to the ground and not the other way around. It's always down the gradient, so from the warm to the cold. It's like you have a river that always flows from the higher place to the lower. That's just physics. Okay, let's look at a thermal image. And you see that this guy, there's a temperature scale, unfortunately in Celsius, but that doesn't matter. And you see that the hairs kind of serves as an insulator, and also the shirt, it's less cold, less hot. And you see that his reading glasses are cold in a thermal sense, so the heat doesn't go through them. And you also see that there are folds in his shirt, and in these folds is air, right? And air is a good insulator because it is a bad conductor. So what we do when we dress, we try to reduce our conduction, basically get insulation. As I said, our skin is 93.2 and outside it's 75, and then that means we have a temperature gradient of about 80 Fahrenheit over 4/100th of an inch. So that is really unimaginable, right? Now let's go to something in nature that we know. You often see that you see temperature in North Pole is higher than Fairbanks or vice versa, and let's say it's 1 degree difference. The bird weight between the two is about 13.5 miles. If you now divide the temperature difference by the distance, you get again the temperature gradient between this time North Pole and Fairbanks. And you see that that's a number that's way, way smaller than our 18 Fahrenheit by 4/100th of an inch. So that's a real large temperature gradient. So that means we get a big heat loss due to conduction by molecules at the scale. So what we try to do is to reduce the conductivity, and we need for that materials. And the conductivity, it depends on the material. It depends also on the temperature gradient, on the density of the material, and the porosity, because the porosity is basically having little air trapped, and that basically means is a good conductor. And here we see the conduction of air is really low, and you see here different materials, and you see that the nylons are really more to cover the veins than to actually insulate women from the winter heat. It's not all that, but also because nobody runs around with cotton wool, but we have it weaved or knitted. And there you can do a white weave, like the sweater of this young lady, or a really tight one, like my t-shirt, and you get more air exchange when the weave is loose than when it's tight. And when you mix the materials, you can even have that these holes in between get stronger filled than when you have just one material, because they have different properties. Okay, the best example of how to get good insulation is the bunny wood, and that's a cross-section through that thing. And you see here is a wool felt to basically hinder the conduction to the ground. And then you see that there are 4 layers here of different wool and also wool felt. And why not just pushing in the wool, but putting layers, is again to have this thin air layers in between that basically mean an extra hindrance for the conduction. And why is this extra force here on, or this extra layer here on the toes? It's because when you walk, the snow goes on there, and when your body would conduct heat there, what would happen is that the snow would melt. The melting takes more energy and basically would increase your the conduction and increase the loss of energy. So that's why there are the extra warmth, thick layer on the toes. So radiation is something that's probably even harder to understand than conduction, but I try to get to real world experience that you know. You know all that the sun radiates through the empty space and reaches the ground, and you feel really good when you sit at pipes and the sun goes on your back, right? That's really good. And everybody, I mean everybody, radiates at different temperatures depending on what kind of body they are. So the Earth also radiates, but at a much lower energy than the sun. So that means that our body does do that, but also our environment. So it gets from space the energy. And don't worry about these numbers. This annual averages averaged all over the globe. There will be probably never a day where it's exactly this, because that's, again, a climate artifact and statistical value. But why I show this is to just tell you the idea that basically when the sunshine comes with the radiation, that some of the radiation gets lost because the atmosphere is dirty, because there are clouds in the way, and then depending on how reflective the surface is, some of the sunbeam gets back right into the sky. So I said also the Earth radiates, but at a lower energy, and so it's radiating with longer wavelengths. And so we have also conduction from the soil, we have evaporation. You remember that when it rains, after the sun comes, goes up, dries. And when we have clouds, then that hinders this transfer of this long wave radiation, and it stays warmer. when there aren't, it gets colder. So that's what our environment is doing. And now let's look at this as a function of the day of the year on this side. So January 1 is down here, December 31st is here. And what we are looking at is the daily sunshine that we can theoretically get if there's no cloud, no dirt, right? You get the idea. And here's the latitude, South Pole here, North Pole here. And so you see that the sunshine we get varies through the year. And now when we look at Alaska, then that's basically here what's now in the box. So you see that in the northern part of Alaska, we get quite some different possible sunshine or radiation from the sun than in the south. So that's just a theory. Now, I said everybody, so also our clothes radiate. Now, think of a day where you are at home. Your home is at 68 Fahrenheit heated, right? So you take your coat, and your coat has, of course, an equilibrium with the temperature in your house. So it radiates at a temperature of 68 degrees. Now you set your foot in front of the door, outside. The outside temperature is given here, Fahrenheit down here. And here is your heat loss. If you go in winter, you will have a larger heat loss as the temperature difference is greater, because then your clothes radiate stronger. And it also depends on the temperature of the clothes. If you have quite gray clothes, then they radiate at a lower energy than black clothes. Now let's do the opposite. We go out with our 68 degrees Fahrenheit clothes into the warmer atmosphere, so summer. Then what happens is that we don't have an energy loss, because now outside it's warmer. So basically now the atmosphere loses energy and transfers that to our clothes. And you have seen that. There's a difference when you are sitting at the bunkhouse in the sun and you have a black t-shirt or you have a gray t-shirt, right? That black t-shirt gets really hot. So, take-home message here is, black clothes are never good. They only make you look slimmer. Okay. So now let's go to the naked body. Yes?
This is regardless of whether the light is outer clothing or inner clothing. Is that correct?
Outside.
An outdoor jacket or how?
An outdoor jacket, yes. I'm talking about, yeah. Now let's go to the naked body. So, if we have a summer day like today, then we lose radiation by heat to the environment. Of course, the environment also gives us heat back. But what I'm just looking at the loss that we do. We transfer air, right? And we have conduction through the air and also convection. And now let's see how that changes percentage-wise when we heat it up a little bit to 86 degrees. You'll see that we now radiate less because we are closer to, our radiation is closer to what we feel from the environment. Then we sweat a little bit more and the conduction gets up. And now let's go into the dark days. 95 degrees Celsius, New York, right? And then all we do is sweat like a pig, right? So you get the idea. Okay, now let's dress, right? I mean, okay, we know that in Fairbanks you only dress in winter to not die from hypothermia, and in summer to not get to trouble with the police, but let's dress, right? Here at the university. So what we have to have is clothes that let our sweat out, because otherwise we don't get that cooling, right? We have energy loss by just breathing. You see that when we have that cloud in winter, right? There you see that. We have the infrared radiation exchange between us and the environment, depending on whether it's warmer or colder, which direction it goes, whether it's a gain or a loss. We have convection, we have the infrared radiation, I said that already, sorry, and we have the conduction. And, well, we can also move. That is also external work that heats our body. And our sun is shining, and it also hits walls and reflects that. So that's basically here the summary of our energy exchange or balance with the environment. So now you have the idea of this model. This model basically calculates the thermal stress that we feel, and it depends on the solar radiation, the sample radiation, the air temperature, the wind, the relative humidity, the clothes, and what we are doing. Okay, all these parameters that I just explained how they work go in there. And what that model spits out is basically a temperature, and it's called the universal temperature comfort for thermal comfort index. Universal temperature thermal comfort index. And then they have correlated that with these environmental conditions and have asked people how they feel. And so they were able to come up with temperature ranges that they then classified into heat stress categories. So we feel good when we are somewhere between 48 and 78 or 79 Fahrenheit, and we don't feel any thermal stress. If it's getting warmer than that, we feel moderate stress, and in the hot days, extreme heat stress. And on the other side, you can also feel cold stress. So kind of get the idea, the darker the blue, the higher the cold stress, and the darker red, the stronger the heat stress, because the next figures will come back to these categories. And remember, green is, you can go, it's fine, right? Okay, this is Fairbanks this year on the 1st of January. Here, that's local time, and the blue is the temperature that's measured actually at the airport, and the red is the temperature of the universal thermal comfort index. And you see that when we are dressed appropriately, which assumes the model, you see that we have, during that night and all the way in the morning, we have the feeling that it's actually warmer than it actually is. Then here after, at around 12, air mass change comes and affects warmer air. As you see, the actual temperature goes up. And with an air mass exchange, you have always associated moisture, different moisture and wind. And so this moisture and wind make us to feel actually colder than it is. Okay? So you get the idea. Now let's look at summer. There we have the 8th of July 2015. I didn't do this one because it rained, and it wouldn't have been different than the other one. And you see that there we can have even an entire day that feels much, much warmer than it actually is. And you see that according to how we feel actually some heat stress, and not moderate, really heat stress here in Fairbanks. So you can see that. Now let's see how that is over the entire year. I took just as an example 2015 again. And you see that over kind of end of March, in early March, it starts that we have the feeling that it's actually warmer than it's on the thermometer. And you remember that's when you really enjoy cross country in March, right? Because it feels so warm because the sun is there. And you see that even in winter when it's really cold, we still often have the feeling that it's warmer than it actually is. Now, let's go back to our climate of Alaska, and we see, we have different climate classifications, and let's see what the thermal comfort index is over these different regions in Alaska. And I picked the extremes, right? I took Ignok Airfield, that's an example for tundra climate like Barrow. I took, of course, the Golden Heartsea, and I took Kake. And that's kind of has a climate as Cologne, right? And here I showed in which climate region they fall. So that has a moderate, humid climate with cool winters. So let's start out with the incoming solar radiation. We saw the theoretical values before in the box, and I said that's what they could theoretically get. When you see this up and down in green for Kake, you see that they have a lot of clouds because they blend out the sun, right? And if you look at Fairbanks, we have less sun in winter here, and in summer we have also, again, when there are clouds, we get less than our theoretical value would give. Our theoretical value would be kind of along here. Okay, and now Ignok Airfield, well, you see they barely get something, despite they have the sun all over the horizon the entire time. And you don't see anything here because there they have all night. So now let's look at the wind speed in blue and the relative humidity in red. And you have to multiply the value on the side here with 10 to get the relative humidity actually in percent, right? So when it says here for relative humidity 10, you multiply that with 10, that's 100, and then you would have 100%, and that's what it represents. And again, over three sides, you see that there is a lot of wind in Ignok Airfield, and we have no wind at all, right? You couldn't run a wind turbine with that amount of wind. It would just stand there. And if you look at Kake, you see that they have also relatively variable wind, but not as strong as Ignok. If you look at the relative humidity, you see that over most of the entire year, the relative humidity is relatively high, except for this period here. And in Fairbanks, we have here our driest time of the year, kind of March, April. And as we get into August here, our relative humidity goes up. And August, that's kind of a month where everybody wants to go because that's our rain season, right? And then it's... Okay, now let's look at the thermal comfort index. We had seen already Fairbanks and see Ignok Field. There you always feel more or less colder than it's actually there. Not really good, right? And if we now look at Kake, we see that they have large parts of the winter where that applies too, that it feels colder. And actually, they have a similar climate like Cologne. I was there. And, you know, I prefer our cold winters over the climate that's in Kake or in Cologne. Okay, now let's see whether it's how often we have basically no thermal stress. Here, Ignok Field, Kake, Fairbanks, and here I took Eagle River because I wanted to take that as a proxy for Anchorage, right? And you see that here in the interior, we actually can have people die from heat strokes because we have times with strong heat stress and at least moderate heat stress. For Fairbanks, Eagle River, and Calgary, we have 40% of the, more than 40% of the time, thermal comfort. And you see that all these regions have cold stress, but not as strong as economic field. So, if we now come to what that means for dressing. If we look again at the relative humidity of economic field, it's in the 80s, right? And it's really windy, so you need protection for the wind. So you need a material that doesn't let the wind in. You also need a water protection because the relative humidity is high. So you need basically huge insulation in winter and light insulation in summer. So how do you do that? You learn that when we create a thin air layer, that basically hinders the conduction and the convection, and that basically creates a layer of stagnant air that has a low conductivity. So you can entrap the air differently. You can entrap that between hair, right, in fur, or you can trap that basically with layering. So what are these? This is obviously winter, summer in barrel. And so what are these people wearing? Layers. So now think of the typical suit from Wall Street or whatever these New York fashionistas that they may have asked in that study with respect to what's the worst dressed city. They have been here with some princess or whatever tour and have seen that, right? They sit in the bus, air conditioned, so they don't know what's going on outside. And they see that, and they are used to dress for the season, right? When it says summer, they run around with their tank top. When it says winter, they do their coat. Then they say we are badly dressed. But actually, we are appropriately dressed because we dress for the weather that's outside and not what a fashion designer says, now it's summer. Now let's look at Fairbanks region. There we have the biggest extreme between the temperatures, right? So we need huge insulation in winter and no to marginal in summer. So what the tradition is, caribou hide with hair in winter because that traps the air. And in summer, you take a hide without the hair, right? And when you don't have the caribou hide, what do? We do layers because we want to create stagnant air that has low conductivity. And we also take these pants that kind of close at the ankle or at the wrist, the jackets, because that encloses the air so that there is no ventilation, right? Okay, in summer, cotton is a good material because we can sweat a lot here, and cotton really lets that go. So now let's go down to Calgary. Remember, it was often 100% relative humidity, and it was windy. And a cyclone comes through every 3 days on average. Of course, not on average, but a lot of cyclones. So what's the best for them is wind protection, right? And shoes with rubber soles so that they don't get wet feet. And a material that is not very sensitive to humidity is wool. This guy is wearing a wool jacket. The wool has the property that the natural oil of the wool keeps the wetness out. And the wool can also take about 80% of its own weight in water weight out before it feels wet. So wool clothes is what these guys have been wearing there. And of course layers, again with the idea of stagnant air in between. So the modern person, of course, now has these outdoor clothes that let the semi-permeable, just in one direction, let the heat, the sweat out, have a mid-layer with fleece that basically serves as the insulation, and then the outer layer that protects from the wind. So now let's make the view to the future. Again, looking at the Köppen-Geiger climate classification. What I did here is I took a climate model run and just ran the model to look at what it would be then. Here for comparison, that was from 1900 to 2000. I had shown that before, and now here is the projection. And you see that there is no need to buy 100 acres for your grandchild so that your grandchild can grow pineapples in Alaska, right? Because you see that these zones, of course, they change, but they change really slowly. And another thing, this is just one of the climate model simulation. Each climate model simulation assumes certain scenarios of the growth of the mankind, of the development of industry, and of globalization, how the commerce goes, whether it's local or global. And so you don't really know what the technology will be in 50 years, right? Did you imagine that when you were a child that you one day would text, right? No. So you can imagine that these are just projections, what would happen if that and that would be the development of the Earth, right? And so, if you just look at these changes here that have been in the past, just assume, okay, it has always been back and forth, so that will happen in the future too. And drink coffee. Okay, now let's wrap up. What's the take-home message? How we feel our environment when we are dressed appropriately depends basically on the heat exchange with the environment that we have that we can't hinder. And the air can feel warmer or it can feel colder as its actual temperature. And here in the interior, you can die from a heat stroke or from hypothermia, despite the odds are more from hypothermia. Alaska does not have one climate. Alaska has climate zones, several climates, and they are quite different. So that can't be the reason for badly dressed. What we need in Alaska is different clothes for the appropriate protection of the elements, and that's quite different when you are down in Juneau or when you are in Anchorage, in Fairbanks, or up in Barrow. The clothing material needs to have low conduction, and it must reduce the convection and the radiation loss. And if you look at the traditional clothing, they are basically built and made for the environment these people lived in. And that's why they are so different all over Alaska. And if you look at Europe, that's the same thing. But you don't think about that Alaska is so big because it's always a little island down off Hawaii, right? So on the long term, the boundaries between these climate zones shift. And they shift depending on the weather. And so my conclusion is that the people in Anchorage, as all Alaskans, dress smartly, and they are not the worst dressed people. They understand the physics of clothes and the energy exchange between their body and the environment. When there is a Chinook in January and the temperature is kind of 40 degrees, we run around in a tank top because the sun is shining and we feel comfortable in our tank top. However, when it's really cold in August because it's raining cats and dogs, well, we labor. And we don't go with what the fashion says that it's now summer season, winter season, or whatever. Thank you. Yes?
Nicole, let me ask you a question that your talk was not about, which is the opposite of Alaska. In the Middle East now, it's like 120 degrees Fahrenheit max on some days. You see people wearing white robes. You see the white would help keep you cooler if the sun's coming in to reflect the radiation. What about wearing a white robe as opposed to wearing hardly anything in the shade? And the shade temperature is 120 degrees. It seemed like the white robe would not help in the shade.
In the shade, you have also reflection of radiation of your clothes. But why you shouldn't run around without any clothes is not because this is not Europe. It's because you also protect with the clothes yourself from harmful UV radiation. And you can't do that all with sunscreen.
You definitely lose less heat by conduction by wearing a white robe than if you had just a bathing suit on. The conductive heat loss would be less.
When you would have the white robe basically reflects, doesn't heat as strong from the environment as, let's say, your skin that is a darker color than white. Does that make sense?
Anyway, we can talk about it later.
Yep.
All the, I'm sitting here thinking it's great that all those ISIS warriors are dressed in black. You know, you see so many tribal women in the Middle East, the only ones that are covered, and they wear
Black.
black.
Well, have you ever thought about that the reason might be, and this is now really bad to say, that they have all these old women wear black in the Mediterranean area as well as in the Middle East, and women get older than men. You get the idea? So you have less problems with having them live long. It's about retirement. You know that the widows have to wear black there, right? Yeah.
I don't know if you have a good feeling for this or not, but I wonder, is there, wool is very good, and I really respect wool, but are all wools equal? I mean,
No.
there's a lot of alpaca out there, there's a lot of cashmere, there's a lot of sheep's wool. I have a sense that sheep's wool is top end, but I don't know for sure. I mean, are all wools created equal?
No, they aren't. The best heat or the lowest heat conduction is the squid, this wool of the musk ox. And how good, and the Alaskan is better than the Canadian, and this is now not some nationalism or something like that. It's basically because here we have either farms where we can come that out, or we have people collect them on the tundra. While in Canada, they shoot the beast, and then they shave the beast, and so they have a lot of the upper wool in there, which doesn't have that low conductivity, because that also serves for other purposes. So privet is having the lowest conductivity, so the best insulation. And here you see I have put Angora wool here. Here I have wool felt that's usually sheep. And you see that I have two values here, an upper value and a lower value, and that depends also on how you process the wool. If you leave the wool natural, then it keeps moisture from outside out, so that's better. And when you comb it a lot, then you get out more of the upper hair, so it's more the lower hair that actually serves for insulation of the animal, and so you get a higher insulation with that wool or lower conduction. So it depends on the purity of the lower wool, right? So the quality of the wool. So wool is not wool, yes. And I don't know whether you know that, but there are now also recycled wool that stems from sweaters that they then rip apart and recycle the wool. And you can imagine that that wool is not that good than the fresh one, yes.
A leather outer with wool inner would be a really good coat.
Yes. I have a coat like that.
Yeah.
I love that coat. Oh, sorry.
Maybe it's, Kibakaside or something like that. Maybe some synthetic construction to trap air. Are you applying that? Or what fabrics can we use, especially in Alaska, that are out of the box? I'm thinking, should we be wearing silk underwear or something like that? What fabrics, maybe something new that has air in it? Is there something we can look forward to instead of what the Mounties wore?
Silk has also low conductivity, so that's a good thing to wear. Silk is good. Feathers are also good, but make sure that you get feathers from goose or from an area where you have a cold climate, because then they have more little tiny branches in the feathers, which basically leads to that it traps more air. So they basically have better insulation. And also when you have shearling, for instance, always look for that you get it from an area that's cold. You don't want that from a beast in Italy, right? Because they have less underwool, and so your shearling will be not so warm than one that you got from a beast that was somewhere in Canada, right? You get the idea?
But there's nothing new on the horizon we haven't heard of that you have that we should be wearing up here?
No, they are experimenting with different fleece fabrics, and there are only some leaks insofar as these are kind of military research for combat, for Arctic combat. Yeah.
There's something up there that I'm unfamiliar with, viscose, is that correct
Yes.
pronunciation?
Yes.
What is that?
That's artificial yarn that's made out from oil, petroleum. Yeah.
Plastic, then.
Plastic. Yes, it's a plastic. Like nylon, it's plastic, right? So, yeah. Yes?
The insulating material that you're looking for that doesn't exist yet, or is just now coming out, is silica aerogel.
That's slowly.
They're starting to use that for.
Okay.
It's not in wide production yet, but a couple companies are starting to experiment with it. What's it called? Silica aerogel. It's a super lightweight foam product.
The idea is that it has a lot of pores to trap air, and on the other hand, it's light, because when you have to slap your munition, you don't want to slap also heavy clothes, right? I mean, what I find the most annoying is the weight of the winter coats, right? Yes.
Oftentimes, like when you're Nordic skiing or something, there seems to be a trade-off between ventilation, allowing perspiration to pass through, insulation, and wind or moisture. And so it's always like a combination of things you have to adjust on a constant basis, it seems to me.
Well, yes. And the bad news is you can't really get perfect adjustment there, because you can only compensate by movement so much of the cooling that you cause by the movement, and basically the ventilation that you cause by moving. Because what you make when you move, it's not a stagnant air layer in it. It gets into motion, right? And so you increase the velocity with which the air travels in there. And when you now have leaks, and you always have them, even if you have the wristbands here, there new air comes in, and it comes faster in when you move, right? So you will have no chance to adjust that.
Right. So, I mean,
And they do experiments with mannequins, of course, that are not the mannequins that go on the runway, but mannequins that are basically, look like an android. They can sweat, and they are heated to body heat, and they can move them, and they can sit them, and they can stand them, and depending on which angles you have, even over the different body parts, different heat loss. So, and they have tried to kind of move that beast, that mannequin, to figure out whether with our metabolism we could basically adjust for the loss or problems we get when we do sport outside. They couldn't get that.
Oh, interesting. Thank you.
Hmm?
The 8-minute rule. So be the temperature you're going to be at after 8 minutes, that covers the
Yeah.
I'm thinking about these materials, and Richard is probably these materials dry and not wet.
Right.
And
it's
that
just the
changes
material, and it's not,
everything.
yes, it's just dry and not wet, and it's just the material, and not put again into a weave, because that weave also, or knit, causes little pores. So this is just the material itself, the yarn, right, the material, but not the clothing. Then when you look at the clothing, you get also different additional, how should I say it, a modification of the conductivity, because you have these little pockets of air in that fabric. Does that make sense?
Well,
So that's just the pure material.
I'm thinking about the cotton gloves that I buy in the winter, and they're actually very warm until a little bit of snow gets on them.
Right. But because they have problems drying, yeah.
So clothing systems, I think, would be an interesting chart. The nylon shell over the cotton, the nylon shell over something else
Yes.
is the system that works.
There are lists also. I didn't show them here because Michelle wanted me to stick more to Alaska than to the clothes. There are also charts that basically from which you can calculate what the conductivity of certain layers is. Yes?
The military spends an awful lot of time and money researching garments for various types of climates. Do you know if they're currently doing anything specific on Alaska?
No, I just know that that's what they came up with.
Yes, they work well.
Yeah.
Natick sent some folks up this past summer to talk to Moelders Training Center, or actually last winter, to talk to Moelders Training Center about the 4th generation of the extended cold weather it's not necessarily specific to Alaska, but it's really everywhere. So yes, maybe.
So these different providers of like polyester and various that kind of materials, and you're saying it's based on the yarn itself as opposed to the weave and the baffles and all these things. Are there any sort of objective tests out there or testing facilities that look at these, so-called something like baffles or something that they're in the weave?
Well, when you have a waffle weave, like that jacket there, then that also traps more air and keeps stagnant air. So you can do a lot with the kind of weave and the thickness of the fabric to which you put that. Yes.
The weave pattern.
Yes.
But different ones make different claims in order to sell their product and to
Right.
more desirable, distinguish theirs from competitors. And is there any objective tests out there or anything like that about the efficacy of a particular weave?
No, basically, the only objective things are this: when you basically take a mannequin that's heated and or to let it sweat and basically do the experiment under these conditions, and that's basically what the science does. And there are two types of mannequins: the ones that actively can sweat, and that means they have a system that when the sweat evaporates, that it just comes new sweat, and others that are just wetted, and when that water on that skin of the mannequin goes away, then it doesn't sweat anymore, right? Because there's no water anymore. And so they get basically different results on that sweating. And that's probably why it's so hard to basically objectively compare that, because they, of course, will always, for their fabric, use that mannequin that provides better results for their fabric, right?
So that, the industry doesn't have any specific test that they...
There are some industry norms, but with respect to certain things, they have wiggle room. Yeah.
Certainly we wear clothing in the wintertime to keep us warm and in the summertime to keep us cool. There's another factor that goes into what we wear, I think you have addressed, and that's odor or smell. Can you speak about the different fabrics and how they retain odor, body odor?
Well, in my opinion, wool always stinks like a dog when it gets wet. These synthetic plastics, as somebody called them, they tend to quickly stink, right? So I think cotton doesn't do that much. But there are also stuff that have a strong odor by themselves, like silk or like wool.
Has anyone done research on that? Or is that just kind of a personal opinion? I agree with you.
No. Of course there is research on that, but I'm not into that smelly.
Okay.
Yeah.
Yeah, I wanted to pass on a vignette because there's been a lot of questions about clothing technologies. And something that I encountered, I taught courses on housing, and I was in Nome one time, and someone brought up the fact that we were talking about Tyvek as a material, which is literally Gore-Tex for houses. It has a very high water resistance, but purportedly a vapor transmissivity. You can sweat through it with a vapor, but it doesn't allow water to pass. You can do this, test yourself. And what Alaskans have adapted is the Tyvek suit that you would wear in a construction zone or a paint or whatever, they use as an emergency exterior clothing device if their snow machine goes in the water in an overflow or something, because you can actually put the Tyvek suit on if you get wet, and it will allow the blower to evaporate through the Tyvek, but you can actually lie down in the snow and not get wet. And so you can cover yourself and survive overnight and sleep in a Tyvek suit. And I said, this is really Alaskan technology, perfected, adapting it as an emergency device, a Tyvek suit. And it's very light, and you can carry it on your snow machine or in your airplane. And I said, wow, that's just really good thinking. So it's a vignette of modern technologies.
Now we have to make it attractive, though.
Well, you just need an Angelina wear it.
Well, it also allows you to sneak up on caribou because you're in white, so that's another reason they like them. So.
Thank you very much.